Hello friends. Today we'll be starting with a new topic on turbulent flows. I just checked with your teachers of advanced fluid mechanics and advanced heat transfer and figured that turbulence has not been covered in much detail in the form that it is required for convective heat transfer in the previous courses. So I thought I'll spend a little bit more time on this topic, and this topic being new and it's not a revision. I would also try to keep the length of the lectures a little bit shorter than the previous ones. So what do we understand by turbulent flow? All of you must have encountered this term, laminar and turbulent, in your undergraduate fluid mechanics and heat transfer courses to a certain extent, and understood that the nature in which the transport phenomena occur, heat transfer, thermodynamic heat transfer, fluid mechanics, shear stress, mass transfer, happen very differently in turbulent flows as compared to laminar flows. Let's begin with fundamental understanding of the nature of the turbulent flows as different from the nature of laminar flows. The first thing that we need to understand is that irrespective of whether the flow is laminar or turbulent, the flow has to respect conservation equations of mass, momentum, and energy. Okay, so there is no exception about conservation equations. In which case, then the next question arises. So the Navier-Stokes equations, continuity, momentum equations that we had derived, and the energy equation that we have been using in laminar flow, are these equations also valid for turbulent flow? The brief answer, the shortest answer is yes, but we will try to understand why we don't use these equations directly in turbulent flow. Okay, so that's another thing that we'll need to understand. That's one of the questions that we'll need to answer in understanding turbulent flow. What is a turbulent flow? We understand that the word turbulent, even in terms of our day-to-day usage, my mind is very turbulent today, or the situation in the city is very turbulent. The political situation of a particular state is very turbulent. What do we understand by turbulent? There is a lot of chaos, there is a lot of confusion, there is a lot of disorder that exists there. But that is not the whole story with respect to turbulence in fluid mechanics, because there is a certain order that is always there. So if I look at, for example, the flow in the wake of a cylinder, okay, so I have a cylindrical pipe and there is a cross flow that goes over it, then this starts shedding eddies downstream of it, and as the flow velocity increases for a given pipe diameter, so the Reynolds number of the flow with respect to the pipe diameter, as we increase it, the eddy shedding frequency increases, and eventually you have a whole range of frequencies, and therefore you get a chaotic looking flow in the downstream region. Okay, so that is one form of turbulent flow. Another form of turbulent flow, if I might, is if I look at agarbatti. I light the agarbatti and hold it horizontal, and I let the smoke go up from it. I'll find that the smoke goes smoothly until a certain height, and after that it starts becoming wavy and disturbed, and after some distance it's a lot more confused, the flow, and after that you don't see the smoke anymore, so it has dispersed or diffused. So you have a laminar region, and because of some disturbances to this laminar region, there is a wavy region, which is the transitional region, where irrespective of whether the flow conditions are steady or unsteady, there is time dependent motion. Okay, and then the extent of mixing that happens between the surrounding air and this increases because of these random motions, and you get the flow turbulent. So the way to understand it is that a flow which is undisturbed, completely undisturbed, that is, there are no fluctuations introduced into the flow, if it is an absolutely smooth flow. Where can we realize that? For example, if I have, let's say, airflow inside a pipe, okay, and if I have the pipe walls absolutely smooth, that is, at up to the nanometer level, smooth pipes, there are no roughnesses of any kind on the pipeline, on the pipes in a surface, and also the flow is driven by some source which does not introduce any fluctuations in it, smooth flow. So there are no sources of disturbances. Then the flow that goes through the pipe would continue to remain laminar until very, very large flow rates. Okay. Theoretically, if there is absolutely no disturbance, then for any flow velocity, the flow should remain smooth. In normal ordinary flows, this kind of an ideal condition is difficult to achieve. Okay. So this has been experimentally verified that the smoother your pipe is, the later, or the transition from the smooth flow to a turbulent flow happens at a much higher velocity. This is something that has been seen. So we can see that it's actually the disturbances that are introduced in the flow that result in turbulence. So one of the input required is disturbance to the flow. But then when the flow is at a lower velocity, these disturbances, they are killed by this viscosity that is present there. So there is a damping force over those oscillations, and this damping force kills the viscosity, and therefore the flow becomes smooth again. So when the flow Reynolds number, which is the ratio of the inertia, which is the momentum of the flow, to viscosity, is within a certain number. For different configurations, this critical number is different. So for a flat plate flow, for example, the Reynolds number based on the distance from the leading edge up to 5 into 10 to the power of 5, that is 500,000, the flow is typically laminar, and beyond that, the transition starts occurring and the flow becomes turbulent. Now, for Reynolds numbers less than the critical Reynolds number, when the disturbance is introduced into the flow, the disturbance is overpowered and smoothened or dampened out by the viscosity. So, beyond a critical Reynolds number, when disturbances are introduced, the viscosity is unable to control the oscillations, and therefore the damping doesn't happen. There is a growth in the oscillations, and that results in more chaotic motion. Okay. So one way of looking at it is a stable flow when a disturbance is introduced. What is the condition of stability of the flow for infinitesimal disturbances? What is the condition of stability of flow for finite disturbances? So this is one way of looking at turbulent flow from the stability of the solutions of Navier-Stokes equations. So mathematically it's looked upon that way, and physically also it's looked upon like until what flow velocities or flow Reynolds numbers do these disturbances that are introduced into the flow get overpowered by viscosity. So stability is one aspect when we look at laminar to turbulent transition. Okay. The second way of looking at the whole thing is that, as we looked at in the example of the incense stick or the agarbatti smoke, after a certain distance, because of these oscillations, this smoke just disperses and disappears, which basically means the rate of diffusion into the surroundings is enhanced by the presence of turbulence. So in some way, this turbulence is an enhanced mechanism of mixing. Okay. So in laminar flow, there is a certain mixing that happens because of the viscosity, because in the laminar flow there is a stream that is going at a certain speed, okay, and there is a velocity gradient because of which this drags the surrounding medium along with it, and so there is entrainment of the surrounding flow that happens. And this is because of velocity gradients. So the velocity gradients, and they have an influence of viscosity, influence effectively this upgoing stream exerts a stress, shear stress on the surrounding medium, trying to take it along with it. Similarly, from the incense stick smoke, where the concentration of the particles that make it visible is higher to the surroundings, there is diffusion or dispersion of particles because of the gradient in the particle concentrations, or similarly the gas concentrations that constitute the smoke and the surroundings. So if there is more CO2, for example, in this pencil that goes up, in the smoke that goes up, the CO2 will diffuse because of molecular diffusivity. So this is what happens in laminar flow. The gradients of temperature, concentration, or velocity result in the annihilation of the gradients themselves. So if there is a more gradient, there is more entrainment, and therefore this velocity goes down, this velocity goes up, and the velocity gradients are reduced. Similarly, when this concentration is higher, this concentration is lower, there is diffusion that happens here, and then this concentration increases, this concentration decreases, and the gradient is killed. So in diffusion phenomena, the gradients are opposed by diffusion that happens because of the gradient, and therefore there is a stabilizing effect. Right? So this is typically what happens in laminar flow because of the viscosity. What happens when there is turbulence? When there is turbulence, there is also additional fluid motion because of these eddies that are getting formed, because there is these oscillations and the flow starts forming recirculating pockets of small eddies, just like what happens in the wake of a cylindrical wire. So when there is a flow that comes on a cylindrical wire, the flow starts shedding vortices here, and these vortices actually then further break up into smaller vortices and eventually disperse. So if I look at any given location, there is no steady velocity in one direction, but there is a fluctuating velocity, and this fluctuation, when the wake passes through that region, the fluctuations increase, and then they decrease, and then they increase, and then they decrease, and so on. So there is a certain additional oscillations of motion which are superimposed on top of mean motion. So the second way of looking at the flows is that there is an additional mechanism of diffusion because of this fluctuating component of motion. So if I have a flow that is going and there is fluctuations in velocity or fluctuations in temperature that happens here, because of that there is additional mechanism of, so if there are two layers flowing and there is fluctuation, so this layer comes and mixes here and this layer goes and mixes there, so there is an additional mixing mechanism between layers of fluids in addition to the laminar motion. So turbulence results in additional diffusion phenomena or additional dissipative phenomena, because the diffusion phenomena is dissipative in nature because the gradients are destroyed. So this is the second way of looking at it. So one is the stability of smooth flow to become disturbed flow. So that results in laminar to turbulence transition. A second is extra diffusion or extra dispersion that happens, because of which mixing enhances and gradients are smoothened out faster, right? So there is dissipation. So this is the second way of looking at it. So people look at it in the form of extra diffusion mechanism or additional viscosity or additional diffusivity that gets added to flow because of the presence of turbulence. A third way in which people look at it is what is called the Vortex Dynamics. This is something I heard that your fluid mechanics course had covered in some detail. So suppose I have an airplane that's flying, okay, So it actually goes through the stationary air. So if I for a moment look at the airplane as relatively fixed and the air is moving over it at a velocity, then in the tail of the in the trail of the aircraft you will find eddies or vortices which are about the size or order of magnitude of the size of the dimensions of the plane components. Okay, so the vortex that is caused by the fuselage would have typical dimensions of the fuselage, the cross-sectional dimensions. What is caused by the wings would have the typical dimensions of the wing, and so on. And then as you go on, these large eddies break up into smaller and smaller and smaller and smaller eddies, finally to the tiniest sizes at which these eddies lose their energy to the surroundings in terms of viscosity. So there is a certain amount of energy that is drawn from the mean flow by the largest eddies, and then these eddies break up into smaller and smaller and smaller and smaller eddies, and finally the smallest eddies dissipate the energy that they have as molecular heat. Okay, so you have a certain cascading of energy from the largest eddies to the smaller and smaller eddies, and finally in the smallest size eddies this energy is dissipated as heat. Okay, so you look upon the whole turbulence as an energy cascade from large eddies to small eddies. So you look at them as vortex motion, eddy motion, and eddies transferring energy from one scale to the other, in the process splitting and dissipating. And finally, all the flow energy is dissipated in the form of heat. And as we discussed earlier, until such time that the Eckert number is not large enough, the dissipation, EC by RE is not large enough, the dissipation of this in the form of heat does not produce a significant change in temperature that we need to include in the energy equation. So it is accounted for in the flow equations as to how the energy cascades from the higher to lower, and therefore you account for it in the form of an additional dissipation or dispersion of the flow energy. That is accounted for in the momentum equations in some form, and in the flow energy equations when you derive it, for example, the Bernoulli's equation and so on, you account for them in some form. But then you don't account for the dissipation in the thermal energy equation because the temperature changes that are caused by these is negligible. But when the EC by RE term is large, then this viscous dissipation also becomes important. Okay, for example, in re-entry vehicles where the velocity of the re-entry vehicle is very, very high, the viscosity of the atmosphere results in very, very high shears at the surfaces. That results in extremely high temperatures being produced because of the viscous shear heating. Okay. So that is an example where you need to consider the viscous dissipation term, but otherwise the viscous dissipation term is not considered as part of the energy equation, but it is accounted for to model the dissipation of flow energy and therefore the dispersion and dissipation in some form in the momentum equations. So a third way of looking at the turbulent flows is in the form of the energy cascade between vortices of various sizes. And so you look at length scales and velocity scales of various sizes. So the large eddies would have large velocity fluctuations and over large length scales. And when you go to smaller and smaller eddies, you have small fluctuations over smaller regions. Okay, so you have fluctuations of velocity in very large scales, medium scales, and small scales. So the entire range of scales will need to be looked at when you need to resolve the entire vortex dynamics in complete detail. Okay, so that is another form of looking at it. And then you try to expand the turbulent flow velocities in the form of Fourier series, because you have fluctuations of all scales and therefore all frequencies. So you look at the flow oscillations or the eddying motions or the fluctuating motions using a series of oscillations of various different amplitudes and frequencies. Okay, so that is a way in which it is modeled. And you also look at large eddy breaking into smaller and smaller and smaller and smaller ones. So you look at it in terms of fractals. Fractals are basically geometrically ordered sizes which look similar to each other but which are smaller in substructures that get formed. So you get patterns of various kinds. So you use fractals to model turbulent eddies and their motion. So this is another way of looking at it. The modeling of these flows using the mass, momentum and energy equations would follow the same Navier-Stokes and energy equations, but then what we need to be cautious about is the range of scales of velocities and length scales and time scales if there is a fluctuation. So turbulent flows become inherently transient in some nature, although the mean flow, if I average it over some form, remains stationary or steady. The details of the flow are always transient. So if I have to capture everything that happens in a turbulent flow, including the vorticity dynamics, the large eddies becoming smaller eddies and dissipating energy and so on, I will need to look at the mass momentum equations in all of those scales. So if I need to capture things in the smallest possible scale, then I will need the grids which are of the order of micron sizes or smaller than that, at which scales the macroscopic or the continuum motion dissipates energy into the microscopic or the molecular motion. Okay, so you'll need to resolve that size or the scale, and at the same time you'll need to resolve the size of an object like an aircraft or aircraft wing or anything that results in the largest size eddies. So your flow will need to resolve the entire computational domain using very, very small grid points and therefore very, very small time steps, because the time scales of the smallest eddies is extremely small and the time scales of the larger eddies are much larger. With the net result that if I look at the computational grid that is required, we looked at numerical solution of boundary layer equations in the last lecture. I had shown you how you divide the domain into control volumes of sizes of the kind that we took in laminar flow. In laminar flow, the grid sizes that you require would be necessary to resolve the gradients that happen near the wall or wherever the gradients are sharp. But in the case of turbulent flow, the resolution has to be to the smallest molecular scales at which the energy is dissipated into molecular levels. This can be of the order of microns or fractions of microns to the largest. So the smallest grid size that you would require wherever there is turbulence would be of the order of sub-micron size. And if I have to resolve, for example, the flow around an aircraft, which is a few tens of meters of length and width, then you can understand in a three-dimensional volume the total number of grid points that you might require. Okay, so when I solve the entire set of mass, momentum and energy equations over the entire domain using grids of that smaller size, we call that as the direct numerical simulation of turbulence. Okay, so computationally, direct numerical simulation is extremely expensive, and therefore even today with the biggest of the computing powers that we have, we may not be able to do direct numerical simulations of very large engineering systems. Even today, the DNS is restricted to small sized turbulent systems, which is of the order of a few centimeters at most, and not in the order of tens of meters or hundreds of meters. Okay. So what that necessitates is that you would need to be able to resolve, for example, the flow around an aircraft with the grid sizes that are commensurate with what can be computed in the today's computers. But then whatever happens in the sizes smaller than a grid size need to be in some form accounted for, or what you call as modeled, in order to capture what happens because of those smaller eddies. Okay. So that gives rise to what is called the turbulence modeling. Okay. So you don't solve the complete Navier-Stokes and energy equations in the full form in all cases, but you try to create models. How do you do that? You do what is called averaging of the Navier-Stokes equations. Okay. So for example, there are multiple ways in which the averaging can be done. The simplest of those is what we call as time averaging. So for example, let us look at the flow over a flat plate, the simplest example that we have been taking. So this problem is a steady state problem. There is nothing that is actually changing with time in the mean motion. But when the flow is turbulent, there is turbulent oscillations that are happening. So you choose a certain time range or a time period over which all of these oscillations eventually nullify the effect of each other. So if there is an oscillation where some motion happens upwards, somewhere else at some other point in time there is a motion that happens downwards, so that the mean remains stationary. This is typically what happens. So you choose a certain long enough time scale over which you integrate these equations and say that if I can write the velocity as a sum of the mean and the fluctuating component, then the fluctuating component averaged over this time period gives me a 0. Right? So that is what we call as averaging of equations. The first of such averaging was done by Osborne-Reynolds in the late 19th century. Okay, and even today, the Reynolds averaged Navier-Stokes equations are commonly utilized in engineering turbulence calculations. So we'll talk about that approach in calculating turbulence of averaging the Navier-Stokes equations either over a time period or, just as I mentioned, grid sizes. So I average it over space, over certain volume in space, saying that whatever happens larger than that grid size is represented by the mean flow, and whatever happens smaller than that grid size we will need to incorporate including models. Okay. So similarly, whatever happens in the mean motion is calculated by the mean equations, but the fluctuating components that result in additional viscosity or additional mixing or additional diffusion will need to be accounted for using modeling. Okay, so this brings us to the concept of what we call as turbulence modeling. So when we do a time averaging, we have what is called the time averaged Navier-Stokes equations, and when we do a space averaging, we have what is called the large eddy simulation. So the larger eddies are simulated and the eddies smaller than the grid size, what we call as the sub-grid scale modeling. Sub-grid scale eddies are modeled using numerical models. Okay, so this is something which brings us to what is called the turbulence modeling in the computational and analytical methods. So you have the direct numerical simulation, which is the most computationally intensive one. Then you have what is called the large eddy simulation, which is not as expensive as DS, but is also expensive. Then you have what is called the Reynolds averaged Navier-Stokes equations, which result in the turbulence models of various levels of complexity. Okay, so we will be looking at the Reynolds averaging and some conceptual understanding of turbulence modeling as part of this course, and we will also understand the analytical methods that were due to Prantl and his co-workers and people who followed him, so that we also get an understanding of how the turbulent flow behaves in the vicinity of walls. So we will be looking at the turbulent flow past a flat plate from that perspective and try to understand that as well. Okay, so now you see that turbulent flow therefore has multifaceted complexities and is understood by different people from different perspectives. So you can understand it from the stability perspective, you can understand it from the dispersion or diffusion perspective, you can understand it from the fractal perspective, you can understand it from the vorticity dynamics perspective, you can understand it from the turbulent computation perspective in terms of direct numerical simulations, you can understand it from the turbulent modeling perspective in terms of large eddy simulation, Reynolds average, Navier-Stokes equations, and then the various models that are born out of the Reynolds average, Navier-Stokes equations. I hope that gives you a broad overview of how turbulence is understood, and if you try to look at turbulence from different angles, it's even today more like the 5 blind men feeling an elephant. So the turbulence is an elephant, and the whole perspective of the turbulent flow is still not completely understood by all mankind, the way they will look at it. Each of them tries to understand it from the perspective from which they are looking at it. And therefore, somebody understands it as a wall, somebody understands it as a pillar, somebody understands it as a brush, somebody understands it as a whatever you call it, the spear or whatever. So this is exactly what is happening today also. The understanding of turbulence is, even after 150 years, Osborne Reynolds' first paper came in the 1880s. So we are like almost 140 years since Osborne Reynolds. The understanding of turbulence still remains elusive. A lot has been understood about turbulence, but a lot still remains to be understood about turbulence. And particularly the turbulence of various scales, looking at the natural phenomena. Practically all natural phenomena are turbulent. So if you try to understand simple turbulent flow in the absence of any heat transfer or mass transfer, that is bad enough. For example, if you look at the turbulence that happens in atmospheric motions, okay, the atmosphere has length scales of kilometers. Okay, and the boundary layer on the surface of the ground has the thickness of meters and tens of meters sometimes. So that's one scale in which you are looking at a boundary layer, a turbulent flow. So the kinds of complexities that need to be understood there. Atmosphere has various strata. You have a hydrostatic head because the air layers are sitting on top of each other because of gravity. You have the heating that happens because the sun's rays come in, and the bulk of the atmosphere is transparent to the bulk of the solar radiation, and therefore the solar radiation directly penetrates to the ground, and from the ground there is re-emission that happens, because of which different layers get heated differently, and therefore there is a stratification of density of various kinds. So you get various additional complexities, and these things compounded with turbulence becomes very difficult to calculate. So the atmosphere calculations and calculation of weather and weather prediction in meteorology is a difficult ball game in itself. So this involves fluid mechanics in addition to heat and mass transfer, because heat transfer due to the sun's light that comes in and then gets re-emitted by the ground, part of it absorbed here, the greenhouse and various things, and mass transfer because there is carbon dioxide concentrations, there are various other gas concentrations, and most importantly humidity, the moisture concentrations. So this is one complex problem in turbulence that is addressed. Another kind of complex problem is, of course, what happens in aerodynamics. So people look at aircraft propulsion and rocket propulsion, and which involve, even if you don't look at the combustion that is resulting in the propulsion part, the drags and the lifts and the various things that are given simply by the fluid mechanics alone are bad enough in complexity. Okay. Now, to that, when you add the additional phenomena of complexity like combustion is another subject which is understood quite limitedly. And when you have impingement of the two, that is when there is combustion happening in a turbulent flow, like for example in the case of a gas turbine combustor or inside an IC engine cylinder, there are two complex problems which are both elephants in front of blind men now come together, and one needs to look at how turbulence affects combustion and vice versa, and that needs to be modeled so that you get engineering accuracy in predictions. So that is another aspect of solving turbulent problems. Similarly, oceanography. So inside the ocean there are ocean currents which determine the weather, the polar ice melting and the temperatures that are created because of that allows the water to sink because it is denser, the colder water. And then there is this whole stream of ocean currents that happen. The water that gets heated in the equatorial region rises up. So the water that sank there comes and then rises here, and then it is also compounded too by the salinity gradients that are there. So you have motion of density driven motion, both because of temperature gradients and salinity gradients in the oceans. And that is another challenge. And then with atmosphere as a boundary condition to it, the oceanographic problems are solved. Sometimes with the ocean as boundary condition, atmosphere is solved, or sometimes a coupled problem is yet to be solved because the domains are both huge and formidable in themselves. So this is another aspect. And in engineering, wherever you go, the flow is turbulent. Okay, you're starting from a simple pipe flow. You might be pumping water from your underground sump at home to the rooftop overhead tank. This pumping problem, the water that goes through the pipe is turbulent, and therefore in order to find out how much is the pumping power required, if I want to fill the tank upstairs at a rate of, let's say, certain number of liters per minute, or let's say the tank of 500 liters, I would like to fill it in about 15 minutes time. Then what is the pumping power required, and what is the kind of pressure losses that we need to encounter, and what is the best pipe size that we should use, in itself gives a problem of fluid mechanics and turbulence, which is probably the simplest one which an undergraduate fluid mechanics student is expected to be able to understand and solve. Starting from this simple to the most complex turbulent flows, you have the range of problems that exist in engineering. So in convective heat and mass transfer, we will try to look at the implications of turbulence to heat transfer phenomena. So how the surface gradients of velocity and temperature affect each other in turbulent flows is what we would be interested in looking at in this course. Okay. So with that long introduction, let me just go to the whiteboard and try to look at the Reynolds averaging of Navier-Stokes equations, because ultimately at the end of the day, we would be solving equations. And in turbulence, most of the problems that we solve in convective heat transfer, we would be solving the Reynolds averaged equations along with models for terms that are not computed directly by the Reynolds average equations. And these models actually typically arise out of some physical reasoning and some experimentation. Okay, so we'll just look at that in the next 10 minutes and then close this lecture, and then we will go into more details from the next lecture onwards. Okay, so now let's move on to the whiteboard, where we will look at the Reynolds averaging of equations. So let us take a 2D transient Navier-Stokes equations. We didn't use this word in the previous derivations that we did. I hope by now you would all be familiar with this. Navier-Stokes equations is the set of the continuity and the momentum equations, 2D transient NS equations with constant properties. So it comes as del rho by del T plus rho into del U by del X plus del V by del Y plus U del rho by del X plus V del rho by del Y equal to 0. And when I say constant properties and density remaining constant, this goes off and these go away. So you just get del U by del X plus del V by del Y equal to 0. So in this, what we try to do is to write U as U bar plus U prime and V as V bar plus V prime. Just to understand it in perspective, suppose I'm talking about time averaging. Let us say this is the time scale, and let us say this is u. Suppose the velocity u has this kind of a behavior. Okay, so what I can do is to average it in such a way that I get a mean flow that is like this, such that this, let us say, is u bar, and therefore if I just plot u minus u bar, the u is this fluctuating thing and u bar is this. So I plot u prime, which is equal to u minus u bar. If I try to plot that here, I'll get oscillations which are like this. Okay, so if I take a time period, let us say, which is something of this size, then I can get u bar as a transient and u prime also as a transient, but integral from let us say, if this I call it a time period capital or rather t, I call it as, let's call this as okay, all these symbols we have used in some form or the other. So let me just call it as some time period Tp. Okay, so integral from 0 to Tp of u prime dt would actually go to 0. So you choose a time frame such that over that time frame these oscillations actually are cancelling each other, and therefore the integral of u prime dt is 0. So then I would get an integral of from time 0 to t or Tp of u dt would actually be u bar, so 1 by Tp if I write here. Okay, so this will be u bar as the definition because the u prime integrates to 0. Okay, similarly the integral of v dt would give me v bar. Okay, and v prime dt also integrate to 0. Okay, so this is what we will do. So if I write u is equal to u bar plus u prime and v is equal to v bar plus v prime, and then do an averaging of this whole equation over time 0 to Tp, then we get the time averaged continuity equation. So del by del x of u bar plus u prime plus del by del y of v bar plus v prime equal to 0, and now I integrate this left hand side and divide 1 by Tp from 0 to Tp. Okay, so the right hand side remains 0. So if I the whole thing multiplied by dt. Now if I look at these one by one, this will be, I'll have an integral of del u by del x or del u bar by del x. Okay, so if I just so there will be an integral from 0 to Tp del u bar by del x dt plus from integral from 0 to Tp of del u prime by del x dt plus an integral of del v bar by del x del y dt, and then plus another integral from del v prime by dy dt. Okay, so all from 0 to t naught. So in each of these, if I interchange the order of the differential and the integral, then I would get a del by del x of integral of u bar dt from 0 to Tp, and this would actually be u bar itself. Okay, and this basically would give me integral of u prime dt, which will be 0, and this will be v bar would come, del v bar, del by del y of v bar would come, and this would go to 0, and so I would get a del u bar by del x plus del v bar by del y equal to 0. So this would be your Reynolds averaged continuity equation. So you find that the mean flow, that is the mean velocity u bar and mean velocity v bar integrated over a period of time over which the fluctuations cancel each other, also obeys the continuity equation, which is written in the same differential form as your instantaneous continuity equation. Okay, so this is what we call as the Reynolds time averaged continuity equation. Okay, so likewise we can also integrate the various other equations, Navier-Stokes equations. So del by del t of rho u, or if I take the rho out, rho into del by del t of u plus u del u by del x plus v del u by del y is equal to minus del p by del x plus mu into del squared u by del x squared plus del squared u by del y squared. Okay, now these terms, if I try to do write u is equal to u bar plus u prime and v is equal to v bar plus v prime, p is equal to p bar plus p prime, and then put in this equation and using the same rules that integral from 0 to tp of u prime or v prime or p prime dt would be 0. Okay, so when you do that, then you'll actually find that this equation also reduces to a form which is very similar to the continuity equation, but there are additional terms that come in which contain u prime v prime bar and u prime bar square. Okay, u prime squared bar. Okay, so basically this is u prime bar and u prime v prime bar. So actually we know that integral of u prime dt is 0 from the range from 0 to tp, but if I square this, then this is actually a positive quantity throughout. So even if u prime itself is like this, u prime square, even when it goes negative, will go positive. So you will have a term which is, so this is u prime, the u prime squared will be all positive. So this integral will not be 0, right? So u prime squared will not be 0. It will only be u prime dt will be 0. Similarly, u prime v prime. So if I have u prime like this and v prime also like this, but not exactly the same distribution, then the product of these two can be at times positive, can be at times negative, but need not cancel out when you integrate it over time. So these terms remain as additional terms. So when you get this averaged equation, you'll have all of these terms in terms of u bar and v bar and del p bar by del x. But in addition, you'll also get del by del x of u bar square, u prime square, and del by del y of u prime v prime. There will be the additional terms that will come in this equation. Okay, so we will write down those equations in more detailed fashion, deriving this and define them in the next class. But I'll just mention in this class that you will have on the right hand side mu del by del x of, or del by del x of, you will get mu del u by del x plus rho u prime squared averaged. This will be one term that will come here in place of this one. So this one term is del by del x of mu del u by del x, which is this part. In addition, you will get a del by del x of rho u prime bar square. Similarly, this term will become like del by del y of mu del u by del y plus rho u prime v prime bar. So this is the additional term that you would get. So each of these, actually this is the viscous shear stress in one direction and the other direction, and these are called the eddy shear stresses. And so the total stress would be called the apparent shear stress. So this whole thing. So this is the apparent shear stress along the plate because of gradients in the y direction, and this is the apparent shear stress along the plate because of gradients in the x direction. Okay, and when we write boundary layer flows, this would be negligible as compared to this, and so these terms will remain and this will go away. So we have to look at what is called the apparent shear stresses, and this we will be able to argue that, for example, rho u prime v prime bar is going to be proportional to del u bar by del y, and therefore can be written in terms of another mu t, which is called the turbulent eddy viscosity. So the constant of proportionality is called mu t, which is called the eddy viscosity or the turbulent viscosity. Turbulent viscosity or the eddy viscosity. So you can actually write this term as mu plus mu t times del u bar by del x, and similarly there will be mu plus mu t by times del u bar by del y. This is the term that you would get. These terms, therefore, these eddy shear stresses are quite often called the Reynolds stresses. Okay, and in 3 dimensions, you will actually get all three. So you will get a u prime squared average, and you will get a you will get a u prime v prime average, and you will get a u prime w prime average. Okay, similarly you will get a u prime v prime average in the v equation, and v prime squared bar, and then the v prime w prime bar, and then you will get a u prime w prime bar, then v prime w prime bar, and w prime squared bar. So these will be the 9 components of the stress tensor, which is called the Reynolds stress. So Reynolds stress tensor, and you can see that it's actually a symmetric matrix because this and this are the same, this and this are the same. This and this u prime w prime and this are the same, and this and this are the same. So you would get a symmetric matrix. So you need to evaluate 6 Reynolds stresses when you come to 3 dimensions, and when it comes to 2 dimensions, you have only these 2 Reynolds stresses, u prime square, and there will be a v prime square. So there will be 3 Reynolds stresses that you will need to evaluate in the 2-dimensional case. Strictly speaking, turbulence is never 2-dimensional because the fluctuations cannot be stopped from off-plane direction, but we can approximate the mean flow to be 2-dimensional and therefore account for the fluctuations in the other directions using the eddy viscosity model. Okay, so this is basically a nutshell of how the turbulent flows are modeled and used. So we will go in more detail about the eddy viscosity model for turbulence in the next class. Because we are already 55 minutes in today's lecture, so we'll stop here. And from the next class, we will go into more detail about these equations and how these equations are solved, and for the Reynolds stresses that we identified or the eddy viscosities that we talked about, How do we quantify or evaluate the values of the eddy viscosity is something that we will do in the next class. Okay. In today's class, we will stop with this and see you in the next class. Thank you.